Section 1.3, evaluating limits. All right, in section 1.2, we evaluated limits. How did we evaluate limits in section 1.2? And how did we solve them? We used our calculator, we built tables, we plugged in numbers, and we made a guess at the limit. And we found that that was pretty good, but I think we saw at least one example where we didn't actually come up with the right answer doing it by building a table. We came very close. We thought the answer was something like 30, but in further investigation, we found out the answer really should have been like 30.26 or something like that. I don't remember exactly what the numbers were, but something happened. So what we're going to do today is we're going to learn how to evaluate limits using algebra, using our vast knowledge of algebra. Yay. And the advantage of using our vast knowledge of algebra is we will always get exactly the right answer, assuming we did our algebra correctly. In order to do that, there are a whole bunch of theorems that we need to know, and I'm not going to write all these theorems down because they're all here in our book. All right, so first we need theorem 1.1. Theorem 1.1 says the limit as x goes to c of b equals b. Why is that true? If I give you the function f of x equals b, what does f of x equals b look like? Like f of x equals 2. What's the graph of f of x equals 2 look like? All lines are straight. It's a horizontal line. All right, so what's the limit as x goes to 6 of 2? 2, how come? The answer is always 2. This is a constant function. This says it doesn't matter what number x is. If x is 6, y is 2. If x is negative 37, y is 2. So does it matter what number I'm getting close to? No, I'm always going to get the answer 2, aren't I? That one's 2. That's all that first theorem says. The second theorem says the limit as x approaches 5 of x is... Well, if x is getting close to 5, then x is getting close to 5. Yeah, I think that one's pretty obvious, right? If x is getting close to 5, x is getting close to 5. So that's what the second theorem says. Third one says, same thing happens if you have x to a power. So if I had the limit as x goes to 3 of x squared, when x gets close to 3, what's x squared going to get close to? 9, right? Because 3 squared happens to be 9. So that's all that one's saying. All right, and then we have 5 more properties down here. And I'll just give examples of these real quickly here in a minute. This one says, if you have some limit and you multiply by a number, then what happens to your final answer? Just multiply it by that number. And this one says, if you know 2 limits and you're going to add them together, then what do you do with the 2 answers? Just add them together, nothing to it. Same thing, if you're multiplying 2 functions together and you don't know each of their limits, you multiply their limits. If you're dividing, you can divide. And if you have a power, you can do a power. So in symbols, these all look pretty crazy. In practice, they're all very simple. I'm just saying things like this. The limit as x goes to 4 of 6x is... When x gets close to 4, 6x gets close to 24. And now if I were to write it out using the symbols of that theorem that we saw a minute ago, they would tell you have to write this. The limit as x goes to 4 of 6x. What this theorem tells you can do is it tells you can take the 6 out front. And then you use the theorem from above that says when x gets close to 4, x gets close to 4. So that's 6 times 4, that's 24. Do I expect you to write out all that work? No, I do not. I expect you to simply apply the theorem, and the theorem says you can just plug the number in. All right, and all those theorems combined say something like this: the limit as x goes to 3 of x squared minus 5x. Well, those theorems all combined say you can take 3 and plug it into this piece, into the x squared piece. You can take 3 and plug it into the 5x piece, and then you can go ahead and subtract your two answers. So what do you get when you plug 3 in there, and then subtract your answers? Negative 6. You get 9 minus 15, which is negative 6. What's the limit? As x goes to negative 1 of 2x plus 5 over x minus 3. Any guesses? Negative 3/4. And how'd you get negative 3/4? All those theorems combined say you take the number and you plug it in. When you plug negative 1 in, what's 2 times negative 1? Negative 2 plus 5 is 3. And then negative 1 minus 3 is negative 4. So usually we don't write the negative on bottom, although there's nothing wrong with having the negative on bottom. It just looks funny to me. So I would write my answer as negative 3/4. So limits are very easy, aren't they? All you do is plug the number in. Wrong? Oh, rats, they get harder? How do they get harder? If this were the limit as x approaches 3, then this problem would be much harder. How come? Because then you can't just take the number 3 and plug it in, can you? What happens when you take the number 3 and plug it in? You get 0, you get undivided. You can use derivatives, but we won't have to yet. We don't know what derivatives are. All right, so when are limits more difficult? Limits are more difficult when you end up with 0 on bottom. So let's do some examples where we have 0 on bottom. Limit as x approaches 2 of x squared minus 5x plus 6 over x squared minus 4. Whenever I see a limit, the very first thing I try to do is I try to just take the number and plug it in. Can I plug in the number 2? No. What happens when I plug in the number 2?
0.
I get 0 in the denominator. It also happens for this problem that I also get 0 in the top, I think, don't I? Because if I plug 2 in, I have 4 minus 10 plus 6. That's 0, isn't it? All right, so sometimes you try to plug the number in. If you get 0 on top and you get 0 on bottom, that tells you you should be able to do some algebra and get things to reduce. So what kind of algebra are we going to do? Do what?
Reverse FOIL, and then you also have square the bottom.
So the proper name for both of those things is factor. So we're going to factor the top, we're going to factor the bottom, and we're going to hope that we can reduce. All right, so we write down limit as x approaches 2. Oops. Of. Can you factor the numerator? Yes, it factors as x minus 3, x minus 2. Can you factor the denominator? Yes. X minus 2, x plus 2. And now a really good thing happens. What's the really good thing that happens? The x minus 2's cancel out. Now can I take the number 2 and plug it in? Yes, I can, because I no longer have 0 down on the bottom. So now when I plug in 2, what do I get? Negative 1 over 4. So there's my limit, negative 1/4. Questions on that? What if the function did not have a 0 on top? Come back next week and I'll answer that question. Because that's not in this section. That will be answered in a section called Limits Involving Infinity. So you'll get some answers that have infinities in them. We'll get to that. Good question. All right, this one. Limit. As x approaches 4 of x minus 4 over square root of x minus 2. Once again, the very first thing I would try to do is I would try to plug in the number 4. When I try to plug in the number 4, some bad stuff happens. What's the bad stuff? I get 0 on the bottom, and it turns out I also get 0 on the top. And that's actually important, that you have 0 on top and 0 on bottom. If you have a different number on top and 0 on bottom, something completely different happens. All right, well, we should be able to do some algebra and make stuff reduce. Anybody got any algebra for me? What's that? I have to multiply by the conjugate to get rid of the square root on bottom. Great words. What's the conjugate? That's right. So what you're going to do in these problems that involve square roots, you're going to do a process called rationalizing. Rationalizing is a fancy word for get rid of square roots. And in order to rationalize, you multiply by the conjugate. Conjugate's a fancy word for change the sign in the middle. So I'm going to multiply by square root of x plus 2 on both top and bottom. All right. Now, when you do this, you're going to have the limit as x goes to 4. Let's do the bottom first. And there's a reason I want to do the bottom first. Something really nice happens. What does the conjugate do? What do you get when you take square root of x minus 2 and multiply it by square root of x plus 2?
Your middle terms cancel, so you just get x minus 2.
Foil it out. If you don't believe me, check it. The middle two terms cancel out. That's why we changed the sign in the middle. It makes the middle two terms cancel out, which gets rid of the square roots. You get x minus 4. Up on top, I'm just going to leave it. I'm not going to foil that out. And there's a very good reason for that. What's the very good reason for not foiling up on top? Because I can see that the x minus 4's cancel out. If I foil it out, it's not going to be easy for me to tell that the x minus 4's actually cancel out. So I reduce the x minus 4's. Can I now take the number 4 and plug it in? Yes, and I get 4. So the answer to that one is 4. Questions on that? Yes?
Can't you just factor x minus 4?
Can't you factor x minus 4? How do you factor x minus 4?
You do root x minus 2 root x plus 2.
Excellent. Alternative solution. Usually not given in textbooks, but this does work. What you can do is you can think of x as the square root of x squared. And then notice what you have. You have something squared minus 4 happens to be something squared. So you have something squared minus something squared. Just like we had back up here, x squared minus 4 factored as x minus 2x plus 2. Square root of x squared minus 4 factors as square root of x plus 2 and square root of x minus 2. So this is the limit as x goes to 4 of square root of x plus 2, square root of x minus 2, all over square root of x minus 2. And once again, we can reduce. And then can we plug in the number 4? Yes. And we get 4. That's a perfectly correct solution. Not the one you usually see in the textbooks, though. In the textbooks, you almost always see the rationalizing trick. Which way should you do it? Whichever way you like better. Doesn't matter to me. I will accept both as correct, because they are. Most of you are probably more comfortable with rationalizing because that's what you've done. That's what's usually taught.
Because it goes a bit more difficult to do the longer, like, square root problems.
Yeah, true. All right, how about this one? Limit. As x goes to negative 3, we haven't used any negative numbers yet. How about x cubed plus 27 over x plus 3? Well, I tried to plug negative 3 in, and when I plug negative 3 in, I get 0 on top and 0 on bottom. So I must be able to do some fancy algebra. Anybody got any fancy algebra for me?
Yep.
Yep. Which is? What's that? There is a rule for factoring cubes. That's correct. Anybody remember it?
At first term, last term stings 9, and you do the square version of it with the opposite sign, and then add them together, and then at the end you square the last one.
You were very close. I think the formula is, there's a formula for cubes. And the formula is a cubed plus b cubed, or if you had a cubed minus b cubed, there's one for each of them. A cubed plus b cubed factors as a plus b, then you have a squared minus ab plus b squared. And if you have the minus in the middle to begin with, all that happens is you get changes in signs here. You get a minus b, a squared plus ab plus b squared. So there's a factoring rule I'm sure you saw sometime in your life, and you probably never used it before for anything. Yes?
B squared in the second one, is that supposed to be positive?
Yes, it is supposed to be positive in the second one. Yeah, it's
Why
only...
doesn't the sign change for that one?
What's that?
Why doesn't the sign change for that one?
Because I need to have a negative b times positive b squared to get my negative b cubed back at the end. If I were to go ahead and FOIL this out, well, it wouldn't really be FOIL because there's 3 pieces over here. But if I were to go ahead and expand this, the very last one would be negative b times b squared, which would give me negative b cubed. So you're right, this sign right here doesn't change. It's this one and that one that change. That very last one doesn't. All right, well, that allows us to answer this question. So this is going to be the limit as x approaches negative 3 of x plus 3, because 3 cubed would give me 27, times x squared minus 3x plus 9 over x plus 3. And then there's no big surprise. What do we do next? Cancel out the x plus 3's. Now we can take the number negative 3 and plug it in, and we get 27. 27. 9 plus 9 plus 9, 27. Questions on that? Anybody got a different way to do that one? How many of you remembered that factoring form? 1 or 2, 3 maybe. Anybody got a different way? Well, that's essentially what happened is we took out the x plus 3, but the big question is what goes there. And unless you remember this factoring formula, you don't know what goes there. Remember, it's not x cubed plus 27 is not the same as x plus 3 cubed. Those aren't the same. Why not? What would I have to do with x plus 3 cubed? I'd have to write x plus 3, x plus 3, x plus 3. When I do FOIL, I'm going to get a whole bunch of middle terms, and those middle terms don't cancel out. So, in fact, this one happens to be, let's see, this one's x cubed plus something. 3x squared plus 9x plus 27, I think, if you FOIL it all out. X minus 3 cubed would be the same, but you would get a minus here, and you would get a minus there. So that one wouldn't work either. All right, there is another way to do this problem. I don't know that it's really any easier, but here's your other option. Limit as x goes to negative 3 of x cubed plus 27 over x plus 3. When you plug in negative 3, you get 0 on top and you get 0 on bottom. What that tells you is if you were to go ahead and divide those two polynomials, you would get an answer with no remainder, since you get 0 on top and 0 on bottom. So do you remember how to do division of polynomials? All right, so what we do for dividing polynomials, we do it like long division. We write down x cubed plus 0x squared plus 0x plus 27. You've got to fill in the missing pieces. It goes from x cubed right to 27. So you need to fill in the x squared piece and you need to fill in the x piece. And then you write your long division bar, x plus 3. So what has to go right here? What times x will give me the x cubed? X squared. So I put an x squared there. Then that's x squared plus 3x. I multiply, right? Just like you did long x. Oops. How about x cubed plus 3x squared? So it's long division just like you learned back in, I don't know, second grade, third grade, except it was letters instead of just numbers, which is a little bit more confusing. Then you subtract. And what do you get when you subtract? Negative 3x squared. And then you bring down the 0x. What times x will give you negative 3x squared? Negative 3x. So that's negative 3x squared minus 9x. And then you have to subtract. And when you subtract, you get plus 9x because you have a minus and a minus. Bring down the 27. What times x gives you 9x? That's a 9. 9x plus 27. And when you subtract, you get 0. So this has to be the same as the limit as x goes to negative 3 of x squared minus 3x plus 9, which is exactly the same thing we had before when we did it by factoring, and you still get 27. Yes?
Should we ever use synthetic division?
Absolutely, you may use synthetic division if you remember synthetic division.
All right.
Much quicker and much easier, actually. But I'm not going to teach synthetic division today. But if you know it, absolutely you're free to use it. Other questions? All right, going back to our book here. We have some more theorems. Limits of trig functions. That theorem says that when you're using limits of trig functions, if you can plug the number in, just go ahead and plug the number in. It'll work. But can you plug every number into every trig function? No, I don't think so, because some trig functions have vertical asymptotes. So we won't be able to answer those questions yet. We'll get to those. So basically, this theorem says, if I ask you for the limit as x goes to pi over 4 of sine x, you're going to tell me the answer is sine of pi over 4 happens to be root 2 over 2. That's correct. And I ask you for the limit as x goes to pi of tangent x. You're going to tell me 1? No. 0, yes. 0. And if I ask you for the limit as x goes to pi over 2 of secant x. You're going to tell me the answer is? What's that? Root 3 over 3. No, I don't think so. Root 3. Nope. So this would be the limit as x goes to pi over 2 of 1 over cosine x. So it is flipped in that sense. And so what's the cosine of pi over 2? Cosine of pi over 2 is 0. 1. Negative 1?
Cosine of 90 is 0.
Cosine of pi over 2 is 0, and 1 over 0 is undefined. So what are you going to tell me? No, you're not going to tell me does not exist. You're going to tell me I can't do that problem yet. Because our theorem said if you can plug the number in, you just plug the number in and you're done. This is one where you can't plug pi over 2 into this function. So the answer at this point is I don't know. I have to come back next week to wait for the teacher to show me more. So the answer here is, I don't know, we can't do that problem yet. All right? So that was a trick question. You cannot take the derivative of that one. L'Hopital's rule will not help. It's not in a form of L'Hopital's rule. L'Hopital's rule would fail for that problem because it's not in the right form. Whatever L'Hopital's rule is, come back and see me for Calc 2, and we'll talk about that. All right, a couple more important theorems in this section. One of them is called the squeeze theorem. Sometimes also called the sandwich theorem. It says if f of x is less than or equal to h of x, and that's less than or equal to g of x for all x, and the limit as x goes to a of f of x is some number L, and the limit as x goes to a of g of x is also the same number L, then the limit as x goes to a of h of x will also be L. What's that mean in English? And how come? All right, this one's easiest to explain in a picture. Okay, so here's our point A right here. And we have f of x. F of x is the smallest function, isn't it? So f of x is down here doing something like so. That's my function f of x. And right here, this is L. This is the point A, comma, L. So when x gets close to A, f of x is getting close to that number L. And then I've got the g function. What's the g function? Well, g is the biggest one, isn't it? So g is up here doing something, we don't know what, but when it gets close to A, it also gets close to L. So it has to do something like that. And then where's h? H is stuck in the middle, always. So if h is stuck in the middle, it can do all sorts of silly, crazy things, but when it gets close to A, what has to happen? It has to go close to that point L2 because it's stuck in between those two functions. So that's why this is called the squeeze theorem. H is squeezed in between G and F. It's stuck in the middle. And also why it's called the sandwich theorem. Why is it called the sandwich theorem? What are F and G? The pieces of bread. And what's H? whatever you like to put in your sandwich. It's whatever in the middle, but it's stuck there. It can't get out. All right, so we're going to have problems that look like this. Let me see if I can steal one out of the book here. Can't think of one off the top of my head.
X sine 1 over x.
Thanks, Ray. I was looking for a different one. I thought of that one, but I was looking for a better one. Limit as x goes to 0 of x sine 1 over x. Ray says will be a good one. He was standing out there spying, I guess. Can I plug 0 into that function?
Sure.
No, I can't. Why not? Because I would have 0 on bottom, so I can't just go ahead and plug 0 in. So what I'm going to do is I'm going to take this thing, x sine 1 over x, and I'm going to squeeze it in between two pieces of bread. And here's the idea. What's the biggest possible value for sine of 1 over x? How big can sine of 1 over x be? What's the biggest possible value for sine? Draw your sine wave. How high up does it go?
1.
It only goes as high as 1, doesn't it? So what's the biggest possible value for sine? 1. So this is less than or equal to x times 1. The biggest possible value for sine is 1. So that's the biggest that function could possibly be. On the other hand, what's the smallest it could possibly be? How far down does sine go when you go after sine? Negative 1. So over here we have negative x. So x sine 1 over x, I can squeeze it in between negative x and positive x. And then, a couple obvious things here. What's the limit as x goes to 0 of x? 0. And what's the limit as x goes to 0 of negative x? 0. So since these two limits are 0, and x sine 1 over x is squeezed in the middle, what does this limit have to be? 0. It doesn't have any choice. It's stuck in the middle. It has to be 0 also. Questions on that? All right, our last two theorems in this section. The limit as x goes to 0 of sine x over x happens to be the number 1. There is a proof of this given in your book. I'm not going to go through it. I'm just going to tell you that that's the right answer, and you can believe me. If you don't believe me, you can go check. Now, okay, once again, I can't just take the number 0 and plug it in, can I? If I plug the number 0 in, what do I get on top? 0. And what do I get on bottom? 0. Unfortunately, with that problem, there's not really any fancy algebra I can do. There's no factoring I can do or simplifying. You just have to look at the book and read it and find out that that really is the right answer. And then there's another theorem. Limit as x goes to 0 of 1 minus cosine x over x happens to be 0. And again, that one's not easy to prove because when you try to plug 0 in, once again, you get 0 over 0. There's not really any algebra you can do to work it out. Okay? So what I'm going to expect is I'm going to expect that you know those theorems and you know how to use them. So your homework problems are going to look like this. You might see the limit as x goes to 0 of sine 3x over x. What we wished happened, we wished that this 3 wasn't here. Because if this 3 wasn't here, the problem would be really easy. If the 3 wasn't here, the answer would be 1. So what we got to do in a sense is we have to fix the fact that that 3 is there. What do? Erase it?
Yeah.
Unfortunately, I can't pull the 3 out. That doesn't work with sine. Because this 3 right here, if I draw my sine wave, what does the 3 right here control? Nope, the 3 out here would be amplitude. The 3 in here controls the period and the frequency. So unfortunately, I can't just take this 3 and pull it out. That's certainly not the same function. This says my period is 2 pi over 3. If I pull the 3 out, it says my amplitude is 3. Definitely not the same functions. So what can I do? Well, it's really pretty simple. What you do is, instead of fixing this, fix this. Make that a 3x. I can put a 3 right there. But if I put a 3 right there, what else do I have to do? I have to put a 3 on top. If I put a 3 on bottom, I got to put 1 on top. Now, notice that this and this match. So now I can go ahead and use my theorem. As long as these values match, I can use my theorem. So what's the limit as x goes to 0 of sine 3x over 3x?
3.
Well, that part's going to be 1, but then we have to multiply it by that 3 right there. So our final answer is going to be 3. 3 times 1, which is 3. All right, one more of those. Limit as x goes to 0 of sine x over 5x. Again, it's almost close. The problem is I have an x here, and I have a 5x down there. I really wish they were the same. Grace?
For the last one, so will that work with any number for the x?
Absolutely. Any number, as long as the number here and the number there are the same. Because they're both going to 0 at the same speed, basically.
So it's always going to be the number that...
Yep, always. All right, so this time the problem is we have an x up here, we have a 5x down there. How am I going to fix it? Do what? I got to get rid of the 5. How do I get rid of the 5? Divide by 5, and then if I divide by 5, I also have to divide sine x by 5. I'm not sure what that's going to do. This one's actually easier. Here's all I'm going to do. I'm going to write this as limit as x goes to 0 of 1/5 times sine x over x. Are those the same thing? Yeah, so there's basically your 2 tricks. If the number's inside with the sign, then you have to multiply top and bottom. If the number's outside without the sign, just rewrite your multiplication. And now I use my theorem. This limit right here is 1. 1 times the 5th is 1/5. Questions on that? All right, I have some very good news for you. What's the very good news? I'm going to give you Monday off. How's that? Here's the bad news. What's the bad news? No, I'm not going to make up for it. But I am going to give you a quiz on Wednesday. The quiz on Wednesday will cover Section 1.2. Okay? So we'll do that right at the beginning of class on Wednesday. Quiz on Section 1.2. Enjoy your long weekend.